Alright, welcome! Today we are talking about extreme values! Alright, so what is an extreme value? Well, an extreme value is basically what is the most maximum a value can be over a domain and what's the most minimum value a function can be over a certain domain. And we're going to talk about this over the next couple of days. Now before we hit this though, before we hit on extreme values, we have to talk about those critical numbers again. Now we've mentioned critical numbers numerous times over the course of the past few weeks. These are where 1, the derivative will equal 0. Or there's another one we really haven't spent too much time on, and that's 2, and that is where the derivative itself does not exist. These are where extreme values occur. Now the reason why we're looking for changes in slopes. When we're trying to find an extreme value, we want to find out where there is a change in the slope. So let's get ready to find some extreme values. So let's practice finding some critical numbers. So of course, to find the critical numbers, we are looking for those derivatives. So that's going to be the first thing we do. So we have this function 5x cubed plus 5x squared plus 10. We're going to take the derivative, and that's going to become 15x squared plus 10x. Now, you can get a point for that in the AP, so you better leave it alone. Next, we're going to find the critical numbers. Now, look how I do this. I'm going to identify these as critical numbers by saying these are critical numbers. And there are two places they occur. The first one is where the derivative is 0 and where the derivative does not exist. Okay, so let's talk about where the derivative is 0. Well, we're talking about a horizontal tangent. When you look in terms of the slope, remember we have dy over dx. This is where the top of the function is 0. For where the derivative does not exist, well, that's when you're dividing by 0. So that's when our bottom of our derivative is 0. And that's where that's where we really like that Leibniz notation. Alright, so if we look at the first one here, if we look at our derivative now, notice we don't have any fraction on this one. So we're not going to worry about any place where the derivative does not exist because there are no x values that will cause this to be dividing by 0. So we don't have to worry about any place where it does not exist. So we can just put no solution there. So we only have to worry about setting our derivative, the top part where the derivative itself equals to 0. 15x squared plus 10x equals 0. Now you're going to factor like an actor. Factor, do not bring that 10x over. I can factor out of 5x, and that's going to leave me with 3x plus 2 equal to 0. And that's going to give me my two critical numbers, 0 and negative 2/3. And that's how we find our critical numbers. So let's try this next one. Oh no, over here, this is a tough one. Now, notice, because this is sinusoidal, they repeat themselves, we're going to restrict our domain. So we're going to have a domain restriction here. They'll typically restrict the domain, especially on trig ones. So we want to find the derivative. Be very careful. This is implicit. Not implicit, sorry. Ooh, bad mistake. This is a chain rule. So when we take our derivative, we're looking at the outside function, which is the sine of 2x. Its derivative is cosine 2x, and we multiply by the derivative of the inside, which is 2. Now, same thing, I'm going to identify that I'm looking for critical numbers by writing it out, CNs. 1, where is the derivative equal to 0? And where does the derivative not exist? Now, just like the first one, are there any values for x that will make cosine not have a value? Of course not. So there are going to be no places where this does not exist. Now notice, even though on the first and two examples, there's no place the derivative does not exist, I'm still going to write them out because I want to show my work. And I want to make sure when I do need it, like for number 3, I have that. Alright, so now when I set my derivative equal to 0, cosine 2x times 2 equals 0, the 2 just drops out if I divide by it. So, and then I just solve this. Ready? I'm really only looking for where the cosine of 2x equals 0. So, to solve this, I look at the 2x and I think, well, where does cosine equal 0? Cosine is 0 is at pi over 2, 3 pi over 2, 5 pi over 2, and 7 pi over 2. Now, you might be asking, why did I go so many? It's because of this 2x. anytime you have this 2x, it means we are going around twice. 0 to 2 pi would be pi over 2, 3 pi over 2. 0 then to 4 pi would be 5 pi over 2, 7 pi over 2. I'm always going to write down double what I really want. And then I divide everything by 2, and we get x equals pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. And then I look at my domain restriction. Ready? Check your domain. Check your domain restriction. That's a DR, sorry. And the only two that work are the first two, 3 pi over 4 and that, because we're going from 0 to pi. But what if this were 0 to 2 pi, we would have to include those. And that's why you want to have these. That's why if this was like 3x, you would then include like 9 pi over 2 and 11 pi over 2. Because what if this were from 0 to, let's say, 4 pi? What would the answer be? We would have to include all of those. The domain restriction here does not determine how far out we go. The 2x determines how many terms we actually need, how many choices we actually get. All right, so let's take a look at number 3. Ew, this one's ugly. Okay, this one's going to hurt. Think test. Think quiz. Okay, you'll see one like this. Taking the derivative, we're going to get, this becomes, what's that? If I drop this down, that becomes 2. I get 10x to the 1/4 minus, and this becomes 2x to the negative 3 over 4. Now, I don't like negative exponents, so I, of course, will write this. This is 10x to the 1/4 minus the 2 stays on top, and the x to the 3/4 goes on bottom. All right, you want this as a single fraction. Trust me, you want this as a single fraction. Okay, so my common denominator is going to be x to the 3/4 if I put a 1 under there, and that's going to give me x to the 3/4 on bottom. On top, this is missing the x to the 3/4, so this just becomes 10x. This already has it, minus 2. And there is our derivative. Okay, to get the critical numbers, remember we have 2 of them. The first one is, where does the derivative equal 0? And then the second one, where does the derivative not exist? Again, I'm showing all of my work. I haven't changed anything. To find out what's equal to 0, well, we know that's just the top. Our dy is 0. And if we do that, 10x minus 2 equals 0. X equals 1/5. Where it does not exist, that's going to be dealing with our bottom. So I set that x to the 3/4 equal to 0, and we get x equals 0. These are our critical numbers right there. All right, go on to part 2. We're going to start taking. So that's our review of critical numbers. Go on to part 2. We're going to start taking a look at what we call extreme values. I'll see you then.